Hi everyone, this video is about linear and angular velocity. This will be leading us into our trigonometry unit. All right, so first we need some formulas and definitions of what these three things are here. This one is the arc length one is really more like for background or review information. So arc length is when you are measuring out the curve of a circle, kind of like taking it and cutting it and laying it flat on a piece of, like on a table, and like measuring with a ruler. So like arc length would be, again, taking like this piece, let's say, of the circle and spreading out flat, measuring with a ruler. So that's like the kind of intuitive way to think of it. The formula though is S equals R times theta. And R can be in any measurement, but theta has to be in radians. I'm actually going to skip over to angular velocity next, and then I'll do linear in the middle. So angular is the speed at which a circle, something circular, is turning. So think of like the wheels on your bike, that type of a thing. Okay. And we need pretty much the same information here. Let me go back over here and label this as theta, and this is R. So for this one, we also need to know what theta is. What you want to think of is then how quickly is your angle turning. So kind of almost think of it like revolutions a little bit. It is what it is. How fast is the circle turning over a certain unit of time? And we would say, or use this as our formula. That is omega. And theta, again, has to be in radians. Well, I shouldn't say that. It doesn't have to be, but you would have to eventually change it to radians to do the linear velocity we're gonna talk about here in the middle. So linear velocity is kind of a combination of the two. Linear velocity is when you are thinking of taking this distance that you've traveled over here, and so you're thinking of how far would that on the ground, if you spun the wheel 20 times, let's say, how far along the ground would you have traveled? So again, thinking about you're riding your bicycle and you're pumping with your feet and the wheel is turning, and that wheel is making you go, that turning is making you go a linear distance. And the formula for this is R times omega. And this is where it's important to know that omega here has to be in radians, but it is a velocity, like a measurement like that. So it has to be in radians per unit of time. One other thing you'll want to probably write down for yourself is what a radian actually is and how we use it in these problems. So a radian is literally the same. It's the measurement of an angle, but it comes from taking the length of arc and dividing it by the radius length. So 1 radian would come from taking an arc length and dividing it by the radius. Any radian measure comes from that same method. So because of that, you can think of a radius also kind of being a rate, where it's a distance divided by radians. Okay, so we're going to use that idea as we move forward with some of these problems. I think that'll make it helpful for you when you're doing some of these measurements. So for instance, up here, when we have these R's in the problem, we would think of this as let's say it's centimeters, so it'd be centimeters per radian, or it's feet, so it'd be feet per radian. Okay. Here's our first problem. We want to find the arc length. That's what S is. So we do this by using the arc length formula, which again was S equals R theta. And I'm going to write that S as feet per radian. This is so we can do canceling when we are doing our multiplication. It'll make it easier, I think, for you to understand what's happening in the long run. Okay, pi over 4 is the measure of the angle. So pi over 4 radians times 12 feet per radian. Those radians cancel. And you are left with 3 pi feet is the distance, the arc length or the distance. For number 2, we're working backwards now. So you've been given S. So S is in 3 inches. And you've been given R. And again, we're going to say that's inches per radian times theta, and we're solving for theta. So when we divide by 10, we're also like multiplying by the reciprocal of this, and the inches will cancel, and we will get 3/10 of a radian would be the angle that would give us that arc length. All right, moving on to the next part. So now we're going to work with angular and linear velocity formulas as opposed to just arc length. Come on, oops. Okay, so first of all, this first part right here, 6 revolutions per second. Anytime you see revolutions, revolutions actually is your angular velocity. It's just not in the right format. So we need to get it into that format. So you want to think about the fact that a revolution is literally going around the circle one time. So one revolution would be turning around the circle one time. And if you think about that in terms of trig or geometry, when you go around a circle one time, you go around the circle a distance of 2 pi radians. So one revolution is the same as 2 pi radians. So we're going to make that conversion over here. We're going to say that our angular velocity would be the same. Well, it is 6 revolutions per second. And I want to get rid of the revolutions, and I know that 2 pi radians are the same as 1 revolution. So that means my angular velocity here is 12 pi radians per second. Okay, now I want to find the linear. And the linear then is just found by taking the 12 pi radians per second. That's your angular, and multiplying by the radius, which happens to be 12 centimeters per 1 radian. And that is equal to 144 pi centimeters per second. Those radians cancel. All right, so the same thing is occurring here. With this second problem, I have 400 RPMs. Let's try that again. Apparently my pens have decided not to work. We have revolutions per minute. That's what RPM stands for. That's revolutions per minute. So I'm going to rewrite it like that. I want to get rid of the revolutions, and I also want to get rid of the minutes and turn it into seconds. So I'm going to remember that there's 2 pi radians for every 1 revolution. And of course, you need to remember that there are 60 seconds in every minute. And notice I'm writing this in this format so everything cancels. So we want the minutes to go away. So I had to put the minutes, 1 minute in the numerator, so it cancels with that denominator. Same thing with the revolutions in the denominator here, so it cancels with them in the numerator there. When you multiply all of this out, I do believe you get 40 pi over 3 radians per second. All right, so then I need to use that to find the linear velocity. So that's going to be 40 pi over 3 radians per second times 45 centimeters per 1 radian. This simplifies out to 600 pi centimeters per second. You could go ahead and multiply out the pi's if you wanted to. It doesn't matter. All right, let's see if I can find a better working stylus here. Next. Oops. So now we've got a couple of maybe a little bit more like word type problems here. So this says there's a point on a wheel that is 12 centimeters from the center. So we have a radius that is 12 centimeters. And that says if the linear velocity of that point Q is 204 centimeters per second, find the angular. So we're looking for omega, and we were given 12 centimeters as the radius, and I'm going to say per radian, so that you'll notice that when I simplify this, I'm going to end up getting rid of the centimeters, and I'm going to end up with radians per second right away in the problem. 204 divided by 12 is 17, so I get 17 radians per second. Okay, next. The minute hand of a clock is 8 inches long. Find the linear velocity of the tip. So remember that the minute hand, you have the hour hand, the minute hand, the second hand. The hour hand takes 24 hours to make one revolution. The minute hand takes 1 hour for one revolution. I am going to say that's the same as 60 minutes, okay? So the angular velocity of this is it goes one revolution every 60 minutes. But we know that there are 2 pi radians in one revolution. So that means we have pi over 30 radians per minute. Now, it doesn't say it has to be in minutes, but I'm kind of interpreting that because it's calling it the minute hand. So I'm going to use minutes. Then the linear velocity will be pi over 30 radians per minute times the radius, which is 8 inches per radian, which gives me 8 pi over 30. I guess I could simplify that a little bit, right? Divide by 2, 4 pi over 15 inches per minute. All right, almost done here. The Earth rotates on its axis once every 24 hours. Rotating is the same as revolving, which means it's kind of giving you the angular velocity. It's saying you have one revolution every 24 hours, which would be the same as 2 pi radians per 24 hours, which could be simplified into pi over 12 radians per hour. That's it. Part B says find the linear velocity. All right, well, we're going to take that angular, which was pi over 12 radians per hour, and multiply it by 4,000 miles per 1 radian. And notice I'm not even showing you guys a lot of work. All this can just be done in your calculator. It's not a huge deal to just write this down and then calculate it with your calculator. I would certainly need to see the setup, but I don't need to see how you got from this part over here to the final answer. This is miles per hour, or it might even make sense on this problem to write it out as a decimal, since that's what we're used to thinking of miles per hour in. So according to our information, the Earth has a linear velocity of 333 and a third miles per hour. All right, I hope that all made sense. Make sure you ask any questions you might have in the question and answer document.